There we go.
So before we, see, I can edit this out. I could swear. No, before we get going, John, our membership secretary, is going to give a brief talk on a Zoom call he had last night about next April 8th total solar eclipse, which is visible from close to here. Do not stay here. Go to at least Hamilton or somewhere, okay? John.
Thank you, Alan. Oh, I have to go. Sorry. Thank you, Alan. Okay, this isn't really a talk. It's just a very, very brief synopsis. We create basically a lot of our members are interested in possibly traveling somewhere to the eclipse next year because the prospects for getting good weather aren't great here locally or where it is visible. And so we have a lot of strategies, and some of us actually want to drive somewhere where the chances are a bit better. Regardless of your interest in the group, if you're a member, you should definitely join a subgroup that we created specifically for the April 8th, 2024 solar eclipse. Not only, we want to keep from overwhelming the main group with messages on it. And I imagine there will be a lot of messaging eventually. Plus, it'll make it easier to find the messages as well, too. So everybody should actually join this unless you hate solar eclipses or something, Anyway, last night we actually had a meeting. The members will have been notified of this meeting. It was on Zoom only. We had 13 people show up, I guess. Of which some of us are pretty committed to traveling somewhere for the eclipse, somewhere along in the US, and others are thinking about it and whatever. We have a recording of the meeting, which I will, if it isn't already, it will be up on YouTube soon and our website, right, Rob? Okay. It's probably there now. Okay, I'll send an email when it is. And so you should watch that if you're interested, and you should definitely join that group. If
also send instructions for joining the group.
I was going to say, there are emails. I think I've included instructions on that in every email that I sent to the group. So if you can't find the instructions on how to join the subgroup, just email me. I'm the guy that sends the meeting notices. Yeah, lots of easy ways to join, actually. And some kind of difficult ways too. So anyway, that's it. Thanks.
I didn't get applause. So come on. Yeah, I got huge applause, but then he wasn't recording. I mean, Rob, did you want to say a few words about what's very colorfully up on our screen? I will click the details and I will get the, so this is on our website, which is mississauga.ras.ca. And I'm going to take you up here later, but you'll notice fairly prominently, I don't like this mouse at all. Where did it go? Okay, there it is. Each year we do hold, hey Shaquille, each year we do hold astrophotography contests. And Rob has put the details up for next year's. And so that you can read up all the information. There are rules and regulations because, what makes a contest like this more fun than rules and regulations. And right back there is one of the previous winners times 7 or 8 or so. There, see right there, see? Yeah, anyway. Oh, thank you. So I can't see what I'm looking at. That's excellent. Okay, so if you are an astrophotographer, or if you're just setting out on your astrophotography journey, I would suggest you look at it because, one, if nothing else, you'll get feedback on what you've done and what other people are doing, but also we do categorize it so that if someone like Shaquille is up against you, you won't be up against Shaquille because you haven't won yet. Shaquille goes into a special category where it's only Shaquille. It's the only way anyone has a chance. No, but we do break it out into previous winners and people who are just beginning. And it's also broken out into several, about 4 categories of deep sky objects or planetary. And Rob, and there's also a youth category. And Rob would have said all this, but he didn't want to talk, I guess, except from the monkey. Yeah, anyway. Okay, so I will now start my talk. Maybe somehow it's a Zoom. I got to go this way, I guess, because you didn't do that for me. That was... And I'm getting that view. So I go that one. Yes. Amazing. Don't believe it. Thank you. You done this before? We're talking now about the Zoom sharing. Is that what you're talking about? Yeah. Okay. Oh, yes. Okay. Thank you. And is it this one or is it that one? Everyone thinks it's this one. Yeah, except I did that before. Yeah. Okay. I'm going to take your word for it. It looks like it. I agree. Okay. So, as I said, I threw this together. I did want to give a talk, perhaps with more preparation, but I did want to give a talk on the telescope loan program to update everyone because during COVID, we built up our telescope loan program a fair bit in terms of the equipment we have. We sold off one piece of equipment, two pieces of equipment, and purchased a number of others. So without further ado, nope. There we go. Okay. I just a quick summary of the specific equipment that we do have, and then I'll go into a little bit more detail about each unit. On the left is an Orion 8-inch Dob. So this is one of the units that we've had for about 12 years, I believe. Beside it is a brand new 8-inch Explore Scientific Dobsonian. They compare reasonably closely. I don't know, Matteo, have you seen both of them? Have you compared both? No. Oh, okay. Okay. Matteo is the manager of the Orion, and I manage the Explore Scientific. On the bottom is our pride and joy, our Lunt 80 millimeter H alpha scope for solar observing. All these come, of course, with mounts that you can render them useful. On the left is a 10-inch F6 Dob that Gord Williams donated. My one note about it right here is that it's large and heavy. So we do not recommend you borrow it unless you've got an SUV or a truck or something, because it's sizable and you want to be reasonably comfortable moving stuff around. Beside that is a 120 millimeter Skywatcher Acromat that was donated by Brian Gibson, as you can see there. We added a Bresser mount to that to make it a reasonably good platform. It's not guided, so it's manual, but still. Another of our new scopes is the 127 millimeter Matsutov Cassegrain, again from Explore Scientific. It ended up that last year we bought 3 telescopes from Explore Scientific. There was this this one, the first Dob you saw, and a special telescope, very similar to one we're having a talk on, which is used for electronically assisted astronomy. And we've had that out at Riverwood. So if you ever want to see your center funds in use, come out to Riverwood and see me present nebulas and galaxies and things. And finally, we have a new donation. As I said, I threw this together. I could not find the name. It was a member that was having to move, and it was a few months ago, and he was desperate for me to pick it up. So I went and picked it up, and it had been sitting unused because I hadn't gotten a case to lend it out safely. But then a UTM student called and was desperate for a telescope so that she could take it to her niece's party. And all of our scopes were out. You see how many scopes we have? They were all out. So I said, well, I have this one. I believe it works. And so she came later that day and picked it up, and it was cloudy. But she has sent me an email since to say that it works well. And in fact, she sent me a picture of the moon that she took with it. So that's great. The neat thing about this one, it's called a Sky Prodigy. And this little piece here is actually a camera. So you unscrew this cap. It needs power, of course, but you unscrew the cap, turn it on and say align, and it takes pictures, does a plate solve. So it figures out where it's pointing in the sky, goes to a new area, plate solves, and then it's ready to start tracking. So it has, a database of 12 trillion objects it can find and track for you. And so it is good for, it's 6-inch, and the optics are pretty good. We added a fairly nice eyepiece to it, so it makes it even nicer. Finally, we do have some sort of miscellaneous piece of equipment that people can borrow. On this page, only the Nikon is out on loan right now, but Ken Patulli donated the Nikon, which is good for astrophotography. You do need to get a T-ring adapter. You need a telescope, obviously, to put it on, and you need a T-ring adapter to adapt to whatever telescope you have. But we plan on acquiring a Nikon T-ring just because we've got the Nikon, and probably a Canon that covers off the two big platforms. We have a collimator for collimating scopes and a sky quality meter. The sky quality meter we lend out so that if you're going to a dark site or a somewhat dark site, you can go and you can take readings. And we ask, if you do that, to send us back the information as to where you were, what the lat long was, and what the readings were, so that we've built up a database of a number of places. It's not as big as I would hope, but we're always on the lookout. We are all troubled by light pollution, and so we have to go further afield unless someone works for the city and can arrange the lights to go up. We had a talk a few years ago about the guy that put in the new light bulbs, all the street lighting, and he said that they were going to be able to dim them after hours, and they would look into it, and they never did. Anyway, so that sky quality meter is useful. So if you are going to a dark site and you want to borrow it, by all means. And the final piece is a C8, which is, it's about from 1980 or so. It is the telescope that I longed for when I was a university student. It was a little beyond my reach. It was donated by Phil Moselle. It does not have tracking. It's 1970s, so no computers, right? It is electronic. It's got like a joystick adapter to control it, so it's sort of funky, but the optics are Celestron optics of that era, which are pretty good. So you saw, as I was going through, I tried to indicate that a good number of our scopes have been donated by members. If you have something, you guys, you got a lot of old equipment hanging around, right? From when you were a child. Yeah. No, if you do have old stuff that you're not using or whatever, seek us out. Little bit of details. Daubs are great scopes for visual observing. You know, they don't track, right? So you have to keep it on the target, but they're great for visual observing. You do have to know your way around the sky reasonably well, although this 8-inch Daub does have a what's called a push to. So if you align it by following some instructions on the handheld unit, then it will tell you to, okay, I want to find Andromeda Galaxy, and you punch in M31. And it'll say, okay, move over 7 units. So you just rotate the thing, 6, 5, 4, 3, 2, 1. Okay, move up 6 units, 1, 2, 3, 4. And normally at that point, it'll be within your field of view, as long as it's a decent field of view. So it is useful for that. And it does, a lot of our scopes have phone adapters, just because you can take pictures, especially with some of the new phones have amazing sensors in them. This is our new 8-inch Daub from Explore Scientific. I added a 2-inch Bresser 30mm eyepiece to this, which gives a really nice wide field view. That Bresser, I should have noted, was donated by Steve Malia of Ontario Telescopes, which was very nice of him. It also has another couple eyepieces. Again, great for visual. It does not have a computerized adapter, so you do have to know your way around or be looking at bright targets. These are the rough details about our solar scope. The solar scope does require more training than the others, in that, 1, it's worth a reasonable amount of money, and 2, it is different from other forms of astronomy. It does have an H-alpha, a tunable H-alpha filter on it. And the use of that is a little, well, you want a little guidance. So we normally go through how to set it up and how to use it, and then how to tear it down. And Matteo now has had the instructions, so he could give you instructions, or Keith has it right now. So it has a very nice Lunt zoom eyepiece with it as well. This is a 10-inch Daub that Gord Williams donated. It weighs about, well, it's a little over 30 kilograms in total. And it is, the tube is quite long. It's 5.5 feet. It's got some nice eyepieces, got a bunch of filters, but again, you do have to be prepared to, you don't want to walk too far with it. I don't think it has a case. I've only seen it when Gord was moving it in and out of his truck. So I'm not sure whether the case made it along with the donation, so I can't say. The Skywatcher 120mm Achromat is a fairly popular scope in our loan program. It's 600mm, so it's like one of Jake's wonderful eyepieces, but his eyepieces are better because he has really nice eyepieces. So it's fairly good for astrophotography again. And this is our new Mac. It is F15. So it's, the really nice thing about it is it has good aperture, and it's very light, very easy to move around, quite small. When I loaned it out the last time, I did not disassemble it. I just left it on the tripod, and you can move it around that way. Just put it sideways. It does have a case. We added a zoom eyepiece to it so that it's quite accessible. And this is the Celestron Sky Prodigy. This setting up for this talk forced me to document what it's got, which is good. So I'll now be able to add it. It's not even up on our website because it was donated quite recently. I do need to get a case for it if I'm going to be lending it out. We had issues with some of our scopes being lent out and they weren't adequately padded. And they saw wear that might have been avoided. So this is quite well equipped now. So as soon as I get a case, we'll put it up on the website and it will be available. No, you can look it up though. It's a standard. It's about 5 or 6 years old now, but you can still find them. I took that picture from someone who is still selling them. They say it's discontinued now. I think they moved to a slightly different configuration. But I mean, obviously well, I would recommend you. My understanding though, from the lady that borrowed it, is that it worked first time. So. How to borrow. One, you got to be a member or a UTM person. And if you navigate directly to member benefits equipment, or I don't know whether I can, I'm not going to bother switching the Zoom call, but there, under member benefits, you can see that, right? Yes. Then equipment loans. So basically what happens is each piece of equipment is listed, and if it's available for loan, it says available for loan. If it isn't available, it indicates it's on loan until a certain date. This is not gospel because I have to get in here and update it manually, and Rob is very cruel. And it's very, very difficult to do. Yeah. 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 But you can see each of the pieces. Again, the only exception is the new Sky Prodigy. Well, new to us, Sky Prodigy. And so if you want to borrow it, you just find one that's available. You click that and it will actually start an email for you with the correct subject line. And you just say, please. And okay, so that's my quick version. Select and click. And that's it. Any questions? No, yes.
Yeah, well, I'm just wondering, what if you don't know how to use a particular type of telescope? Is any training provided, or?
I almost invariably will set up on my, I manage 4 of these scopes and the EAA scope. So people generally come to my driveway to pick these up. And I will, at the very least, give them a, here it is in the package. This is how you open it. This is how you set it up. This is how you point. This is how you tear it down. This is how you stow it correctly. In terms of finding objects and stuff, it's daytime when they pick them up. So, there's not too much I can do. But the other thing I would say is that it hasn't been announced yet, but we will be having a Riverwood night for members to bring scopes that you might have purchased or UTM people to bring scopes that you're having issues with, or you just want to use with other people and help out and show. So this will not be like our normal Riverwood nights where there are 250 people from the public and you get lineups and all that stuff. Hopefully, it will be members only plus some Riverwood volunteers that want to look through scopes and know how we work. And so I would say anyone that has the scope out while that's going on should bring it to that night. And
thinking of buying a telescope would be a good idea.
Sure. But the other thing I would suggest, certainly if you're a member, you should try the various scopes you're thinking about. These are free, right? So we have most kind of scopes represented, right? We have a refractor, we have Dobbs, we don't have a Schmidt-Cassegrain. Well, yeah, we do have the C8, but it's not quite what you'd get with computers nowadays. But so we have certainly optically the majority of different types available for you to try first. So if you've been told you got to get a Schmidt-Castle grading or you got to get a Daub, starting off with, I would strongly recommend people start off with Daubs, but people should try something else too, right? Because Daubs are convenient, but this little Mac is really nice. It's very portable. So it all depends on what you're going to be doing, right? Are you going to be looking at planets? Are you going to be looking for deep space objects? You know, anyway. Anything else? Yeah. Oh. No, I thought there was one up here, but.
Publication or something that we recommend for people to learn about different types of telescopes?
Terrence Dickinson, Night Watch is, we will send out, we haven't finalized the date that someone was talking today. I heard the 13th or the 20th. 13th is way too soon. So it's going to be the 20th, I would think. But just today, Randy was talking about it again. So he's up at the cottage. So what does he care? Okay. If there are no more questions, I will turn it over to Leah, who will.
Oh my God.
The other thing I will do is stop sharing. Well, you know what you're doing. It's lovely. You must have taken that course.
What's the course?
The course on AD.
I think because you're signed out.
Yeah, you want to send it down.
Okay, I'm gonna let you guys adjust things here, but I'm really pleased to introduce a couple of my students, Dana and Rui, who both worked with me over the summer. We were working on trying to develop some instructional materials using the EV scope that the CPS department purchased a couple of years ago. So Dana and Rui worked really hard over the summer doing the initial observations with the EV scope and then designing 3 labs that students can do. And 2 of those labs I'm incorporating into my classes this semester. So we're gonna do a trial run. But another thing that's really cool is that if you have an EV scope or some of these other telescopes, you may also be able to do projects like this if you're interested in them. So that's kind of cool. And I will let them take it from there.
Hello, everyone. My name is Dana, and this is.
Hi, my name is Rui.
And our presentation is about enhancing astronomy education with digital telescope labs. We all recognize the power of hands-on learning. It can boost our confidence, deepen our understanding, and cultivates critical skills. Our research revolves around enhancing astronomy education through immersive hands-on experience by integrating the EV scope, which is a beginner-friendly smart telescope. We were able to craft 3 labs that will observe the sun, a satellite, and an eclipsing binary system. These labs foster skills in target selection, data analysis using Python, and spatial reasoning. This approach amplifies self-confidence, self-efficacy, and comprehension. We will now talk a little bit about the EV scope.
All right, so I'll talk a little bit more about the EV scope. So as you can see here, that is an image of the EV scope. And is there anything special about it? Well, there is actually a lot of special things about it. So other than it being basically, it has a proprietary software. There's a proprietary software where it filters out the light pollution from cities. And it also has an automatic star finder with a database of a few million stars. And the best thing is that you can use a phone app with it. So I understand the Cub has a Equinox 2. The difference between the EV scope and the Equinox is that the EV scope gives you a better resolution. And the image was taken by us. So I think if we submit this, we can probably win the competition as well. Anyway, okay, so moving on to the labs. So the first lab that I designed is actually a solar rotations. So a lot of times when students think about astronomy, they think about, stars, night skies and stuff, but you can do stuff in the daytime as well. And I'm pretty sure students don't want to stay late at night to do stuff. So we have a project that they can do in the daytime. So this solar rotations, basically what it does is they'll look at sunspots from the sun and then observe it over a period of time. And they will just basically see the sunspots moving over a few days. So with this rotation, with the movement of the sunspots, hopefully they can realize that the rotation of the sun is actually not uniform. So going from north to south, it's much faster at the equator as compared to the poles. So the difference is around 30 days at the poles and around 24 days at the equator. Don't quote me on this. I don't remember. But yes, there's a difference in rotations. So what we want them to do is to take photos, get the data, process the data, have some basically come up with their own errors, ask them to evaluate errors, and then to perform data analysis. So the kicker here is that the equation that the rotation is modeled after is actually also made with observations. So there is no definite theory equation that they have. So we can let them do a similar thing. So instead of using the standard equations, okay. Yeah, all right. So instead of like using a standard equation that's provided by the textbook, they can come up with their own equations to model with their own data that they have collected. And in the process, hopefully they'll learn how to basically plan the observations, avoid rainy days, avoid cloudy days. They have to also analyze errors. And the process, hopefully they will, find some interest in astronomy and continue on to further courses. Right, so moving on to the next project. So the next project is a satellite dynamics lab. So students will be asked to measure the orbital period of an artificial satellite. So the image here on your right is a Starlink satellite taken in a single frame. So just from this single frame, we can basically determine what is the satellite dynamics, although it seems like a very long jump now. But to run through the process, so what we want to do is the first step would be to ask them to calibrate the field of view of the telescope itself with the moon. So now they know what, let's say, how many pixels matches to like how many arc minutes of the moon, because we already know how big is the moon in arc minutes. So once they have this calibration, they'll just take a single frame of this and they'll measure the distance of the streak, which is the satellite itself. So with that, in this process, hopefully, they can take logs, they can learn how to use coordinate systems, and they also have to do pretty much almost everything as mentioned in the first lab as well. So hopefully with this, they can apply what they've learned in class and also get more interested in astronomy and know that it's not just about stars and galaxies. Ooh, sorry. Yes. Oh yeah. In the process, I realized something. It's like geometry was pretty tough. So we were observing this from the surface of the Earth. And most of the time when you do physics problems, it's given to you relative to the center. So they will have to figure this out as well. Right. Now I'll pass to Dana for her own project.
So I designed the eclipsing binary system lab, and essentially students will be measuring the light curve of an eclipsing binary system and determine its orbital period. Students will be choosing an eclipsing binary system from the TESS catalog, which stands for the Transiting Exoplanet Survey Satellite Catalog. And from there, they'll be choosing which target is suitable to observe by looking at what certain properties they're trying to search for in order to see that target in the sky. Essentially, the learning outcomes for this lab is that they'll plan observations, collect data, and perform data analysis. So in detail, for planning observations, they have to ensure that they're choosing the right target and that it's appropriate to see in the sky. They have to also mentally map out the local sky so they know which target they're looking for, and essentially like placing in their mind what exactly they're searching for. As for collecting data, students will have to make sure that they're taking accurate logs, so the time, place, and what they're looking at. And for performing data analysis, students will be using Python to analyze these FITS images of their targets and perform aperture photometry and measure data as well and fitting models to a data. So on the screen, we see a FITS images with four sources. So the top center source is the eclipsing binary system, and we have 3 reference stars. And these reference stars are really important, and students will understand why they're important because they'll be using it to create a reference light curve in order to remove the noise from the light curve of the eclipsing binary system. So this is the light curve from TESS, the same light curve that the same eclipsing binary system that I was observing. And we can see here how it frequently, we can see variations of brightness, and we can see it frequently. And students will be able to compare their light curve to the TESS light curve so they can see and analyze the differences and compare the patterns and trends as well. So future applications. So we want to incorporate these labs into this upcoming year and into the astronomy courses. And we want students to essentially be able to communicate with students and be able to collect data and analyze that data as well. And we hope to see the outcomes as shown in this flow chart, that we hope to see an increase of a positive attitude, a more motivation in science, and as well an increase of confidence within them and self-efficacy when they're performing this lab. So some questions that may be asked to students after completing the lab is how confident they feel in the material after completing this lab, from a scale of 1 to 5, 5 being good and 1 being bad, and more questions and of how they feel throughout each of the lab that they have completed. Thank you for listening to our presentation.
Yes. Couple questions. First, a technical question. Did your scope come with a solar filter, or did you add one?
So Prof. Dia bought another alternative solar filter with it.
Okay.
Yes.
And secondly, where you got the combined, those, are you doing it? Yeah, one forward. Are those simply measurements taken from individual frames, individual 1 second or whatever?
Essentially, the satellite was observing this eclipsing binary system for a period of long time, I believe. And essentially, this is like the plot of that time period with the brightness as well.
Right, but if you're going to be doing the analysis with the telescope, you are anticipating that the students will take individual frames and watch for the dips.
Yes, they're looking for the dips, exactly. So it's not for a long period because we want them to observe either 30 minutes or 1 hour. And so it's gonna be like a really short of the curve, yeah.
Lots of students.
Yes.
Can you clarify here, the eclipsing binary and eclipsing binary star or an eclipsing planet?
We're looking at a star, so 2 stars that are orbiting around each other.
Just to add to that, reference star with the binary reference point of the brightness and compare against for the light curve.
Essentially, like the reason why we have reference stars to remove like the noise from the atmospheric background from our observation of the eclipsing binary system. Yes. Yes.
Sorry, and you're anticipating running this single scope, just carefully plotted out in terms of time, allowing for cloudy skies in Mississauga. Is that what they're telling you? Because we know it can't be
That's true. Yeah, it was a bit difficult, but we tried to find dates that were suitable to observe, but yeah, it is very difficult. So yeah.
Oh, gosh. Take 15985.
Oh, yeah.
How to know that it's a very faint star, so for us visual observers, if we could find it, would be, I mean, it's pretty fast period. Would we be able to notice the difference about a 1/3 variation over the course of several hours, if we could see it visually?
I'm not sure, but it was really faint, so
Yeah.
I found it difficult to see it like without the UV scope. So because we live in Mississauga, so like it's cloudy, so it's really hard to see. Yeah. So I don't know if we would be able to see the difference without the UV scope.
You know, the limited magnitude of the UV scope.
I think it's 18. Okay. Let me look it up.
Yeah, it was like
Can we use the eyepiece? The Nikon eyepiece?
we didn't use
No.
we didn't-
As in, I'm confused, and they said, I don't think I looked for it once. It's very related to the point, I don't understand what it means.
Oh, that's input catalog. So this is that from the test? Data mission is the test, so
Mm.
and the guys use the test input catalog for all of the catalog.
So this is a primary start, even though the test satellite is looking for exoplanets. That's what I found.
Yeah, it's kind of able to find even more easily. So it's a whole round.
Yeah.
Yeah, so I looked it up. The limiting magnitude is indeed 18.2 for both the equinox and the EV scope. No. I think the 18 would probably be for like optimal conditions.
Hey. Cool. So I can't give quite as much of an introduction to Joseph's research because he worked with somebody else, not with me, but Joseph was a student in my astronomy 221 and 222 classes last year. But he got a very prestigious summer undergrad research fellowship at CETA over the summer, the Center for Integrated Theoretical Astrophysics. Is that what it stands for? Okay. And so he spent the summer at CETA doing research with Joanna, I guess, and he will tell you about that now.
Thank you. All right. So thanks, Dr. Hirsch. My name is Joseph. I am a current UTM student. Yes, as she mentioned, I did have the great privilege this summer of working at CETA as a SURF student, a summer undergraduate research fellow. And I worked with my supervisor, Joanna Zelko, who's in the top right corner. And my project title is how the 3D dust temperature maps how the 3D dust temperature maps correlates with 3D stellar luminosity fields. So if that's a lot of words, I'll try and explain it to the best of my ability. And I should preface, if you do have questions during my talk, feel free to put up your hand and I'll try and get to you and answer your questions. So let's start off with, what is interstellar dust? So interstellar dust is hundreds of millions of tiny little graphite and silicate grains. These grains range in sizes from like nanometers to micrometers to like even single molecule sizes. And they come from the supernova explosions and the death of stars. And the very technical term is when a star just spits out its guts. Basically, it's just all of the dust and gas inside of the interstellar medium. And this can be repurposed into making new stars, which is something that I'm personally really interested in, and I hope gets further research in the future. So the two main ways we classify this interstellar dust is from its absorption of UV radiation. Observationalists hate this because it's called reddening, because the incoming light gets reddened and shifted to longer and longer wavelengths. The other way we detect this dust is from its re-emission of that energy in the far infrared. So basically, it takes all that energy and re-emits it. So from the absorption of the UV, the reddening, this is a video made by Gregory Green. It is basically, he took a lot of data of the dust and the reddening, and the camera is doing a 25 parsec loop around the Earth, and is faced at the galactic anticenter. And then my supervisor, Joanna Zelko, she took the same map. She mentioned same point of view, but this time she used the emission data from the Planck telescope to reconstruct the temperatures of this interstellar dust. So same point of view, like I said, but the bright blue areas correspond to 25 to 30 degrees Kelvin, and the bright red areas correspond to lower 10 degrees Kelvin dust. All right, so, oh, did I skip the slide? No, I did not. Anyway, so some terminology before I begin, and some little info. How we project the sky in 2D. So if you imagine we have the celestial sphere, and we want to image it on like a 2D plane. So we use the package known as HealPi, which basically splits the sky up into 12 little diamonds, as you can see in the top left. So we have 12 little diamonds, which represent the whole sky. And each of these diamonds get further split into little pixels. And these are called ensides. And these enside just means the number of pixels on one side of the diamond. So for the reddening map, the first map that I showed you, it has an enside of 1024. What that basically means is that for each diamond, it has 1024 squared pixels. And for the temperature map, it has a lower resolution of 128, an enside of 128. So these pixels are important because later when I calculate correlation coefficients, I'm taking the values of each of these pixels and plotting them on a graph to see their correlation coefficients and the slopes. All right, so now that we have the 2D sky projected into, I guess, a 2D plane, now we want 3D distance values and all of the data. So how this was taken was all of this data was binned logarithmically through distance. So as you can see here, basically what that means is that for further and further away distances, it has more and more data. So for the base star reddening map, it has 120 distance bins ranging from 63 parsecs to 63 kiloparsecs. And for the temperature map, it has 17 distance bins ranging from, I believe, 150 parsecs to 15 kiloparsecs. So this is important because if we're trying to correlate the stellar radiation fields with the dust temperature map, we don't want to lose all the precision that Gaia gives us from positions and all of the temperatures, right? So what we do is we use the reddening distance bins to calculate these stellar radiation fields, and then sum them over the temperature map distance bins. So we get an integration over that whole distance. All right, so what do I mean when I talk about stellar luminosity or stellar radiation fields? Really simply, I just talking about the star's luminosity, which is the equation on the bottom left. It is related to 4 pi times the radius of the star squared times the Stefan-Boltzmann constant and the temperature of the star to the 4th power, or simply just the relation between r squared and t to the 4. I don't know, that alpha kind of got messed up. Sorry. So where am I getting this data? I'm getting it from the Gaia mission, which is a really, really big mission launched by the European Space Agency. And basically, it obtains the 3D positions of stars really, really accurately from getting their galactic longitude, their galactic latitude, and their parallax. So that gives us the 3D data. And like from the equation I showed you before, we need the temperature. So the temperature was obtained from Gaia's own calculation from a method known as GSP photometry, which is an MCMC chain. That's where we're getting the temperature. We could also get the radius from the same method. However, from testing, we've realized that it significantly decreases the sample size of the stars and just kind of messes with all of our data. So future work, we're hoping to derive these radiuses directly from the Hertzsprung-Russell diagram by assuming all the stars are on the main sequence. We could also take the luminosity calculated directly from Gaia from a method known as FLAME. However, you can see in the graph to the left, credit to O.L. Creevy, it is the dotted brown box, and it also covers significantly less area than we would hope or we would want. So for this analysis, I should mention, we're only using the temperature that GSP photometry has given to us. So why am I focusing on star formation regions specifically? First of all, in the dust temperature map, it was created with a Gaussian prior. So what that means is basically all the values that we're sort of uncertain about, we just assign them to a Gaussian center point. And the values that we are more certain about have a wider spread. So star formation regions have a really, really good spread in this 3D temperature map, which gives us slightly more confidence to believe that it is correct. And also, it's just a great precursor for future star formation research. And it's just something that's really cool because, I don't know, personally, I don't want to just look up randomly into the sky. All right, so what am I doing? I'm trying to see if the 3D temperature map knows about stellar radiation, or in other words, if we can map these stellar radiation fields to the 3D dust temperature map. So the first method I use to try and do this analysis is called the pixel luminosity tracer method. So like I mentioned before, if we imagine this cube to be a pixel with the galactic latitude, longitude, and the distance, same distance bins, what I'm doing is basically counting all of the stars in this pixel, taking their temperatures to the 4th power, and then summing them all up to get a single value. That's the value projected on the pixel. So now I'm going to show you some of the results that we've gotten from this method. First one we'll see is the Perseus region. I'll explain this really briefly. In the bottom left, you'll see the reddening data in the 6 distance bins that covers the dust temperature map that's in the bottom right. And in the top right, you'll see the luminosity tracer pixel values that we've calculated. So like I mentioned, there's 6 of the luminosity tracers and 6 of the reddenings because we're going to sum them all together to have the equivalent of the amount of data that's in one dust temperature bin. I hope that makes sense. We've also done this. So this is the summed up versions at the top. So on the left, we have the summed reddening in those 6 distance bins. We have the summed T to the 4 values, or luminosity tracer values in the middle, times the reddening, which is basically just giving us the values that that reddening would be giving us based on the density of the dust. And on the top right, we have the dust temperature multiplied by the reddening again. And that's basically just the map that you saw earlier. So for the Perseus region, if we're taking all of these pixel values and plotting them on a graph, we can see that we get a Pearson correlation coefficient that's relatively good, 0.85, and we get a slope of 1.03. These are all good, but as you can see in the graph, there is quite a bit of scatter. So, sorry. The next region I'll show you is Orion B. The reddening slices are 31 to 36. Same thing on the top, you'll see the reddening. On the bottom, you'll see the luminosity tracer values. And on the right, you'll see the dust temperature values. Same thing, we calculated the correlation coefficient with the summed reddening, the summed T to the 4 values times the reddening and the dust temperature map times the reddening. And we get a correlation coefficient of 0.85, and a slope of 1.02. Once again, not bad, but there is a lot of scatter. And I think the last region I'll show you is Orion A. Same thing in the top right, you'll see the dust temperature map. Right below that, you'll see the 5 reddening bins, I should say. And underneath that is the 5 luminosity tracer values. Same thing, calculate correlation coefficient. This one is slightly messier, and we get a lower correlation coefficient, and there's a lot more scatter. So something really cool that I also want to show you guys is, so if this is an image of the top right of the Taurus star formation region. On the left, you'll see reddening. In the middle, you'll see the dust temperature. And on the right, you'll see the sum T to the 4. If you look at the, I can't point, but if you look at the bottom, slightly to the right of the center, there's a really, really hot spot in the dust temperature map. And this is right, you can see it perfectly in the luminosity tracer method, right? And we believe this is the Pleiades star cluster. It's super cool that we can see this. And just wanted to outline that. We only figured that it was the Pleiades star formation region like a month ago, so. It took us a while. We asked a lot of professors and they couldn't tell us either. So what are some limitations to this pixel luminosity tracer method? First of all, the high T to the 4 values are in areas where there's no dust. So if you look at the really hot spot in the top left, it's right in the region where there is no dust. So if we're taking the value of the dust, it's going to be essentially 0, and we're ignoring these really, really hot stars. Another problem is we're not truly accounting for the distance bins in front or behind of the slices that we're taking. So for example, if we look at the Taurus region, that initial star cluster we see really, really well. But just to the right and slightly above, there's another hot spot, but we don't see anything there. So this is something that we're trying to fix with the next method, which is known as the interstellar radiation field method. In this method, in the very center, you'll see a pixel. The cube is representative of a pixel. And what we're doing is we're basically setting a center point for that pixel based on its galactic latitude, longitude, and distance. So we set a very center point. We then define a sphere around that center point for which we're going to consider stars to affect this pixel point. And basically what this is going to do is for all of the stars inside of this big sphere, we're taking all of the stars, same thing, taking their temperatures to the 4th power, and then dividing it by the distance from the star to the point squared. So calculating this distance from the star to a point is slightly non-trivial. I thought it would be simple. It is not, as my supervisor told me. But the triangle in the very center is correspondent to the center of the circle to the star and the point. And the kind of curvy little thing on the right is from the very top of the celestial sphere to the star and the point. So with the help of spherical geometry and Euclidean geometry and all of that stuff, and little messy details, we get the distance from the star to the point. Just trust me on that. So now let's go on to the results. Same thing, I'll show you the Perseus region first. In the top right, you'll see the stellar radiation fields that we calculated this time. In the bottom left, we'll have the reddening, and in the bottom right, we'll have the dust temperature. So I just personally, I'm gonna leave it here for just an extra second because it looks pretty. But moving on to the correlations that coefficients that we calculated, look at that line. It is very good. And I remember creating it and I thought this must be fake. But anyway, this is the period, we get a Pearson correlation coefficient of 0.98 and a slope of 1.00. It's a really, really good correlation coefficient. And I should also mention, these are the summed stellar radiation values for the 6 slices that I took. And they're also multiplied by the reddening again. And just by eye, you can see that they're relatively similar. Might be blocking it. The middle is the stellar radiation times the reddening, and on the right is the dust temperature times the reddening. So same thing, Orion B is up here. And something really cool I think you can see from this, from the stellar radiation plots that I made, you can already see kind of like the structure of Orion B on top of these really hot regions, which is really, really cool. So calculating correlation coefficient, once again, much, much better, 0.92 or 0.93. You get a slope of 1.06. And there is a slight little tail that we get from this correlation plot, which I hope to uncover soon, to be determined. And finally, Orion A. So once again, you'll see the stellar radiation on the bottom, reddening just above that, and the dust temperatures in the top left, top right. Correlation coefficient, much better than before, still slightly scattery. And we're hoping to further uncover why this is in the future. So I should also mention that I'm trying to recreate that 3D dust temperature map that you saw at the beginning with the temperatures of the stars included. This is just for visualization and is really, really cool. And something else that I'm trying to work on, hopefully the code works well, but I'm trying to zoom in on a specific region. So hopefully one day in the future, we'll be able to zoom in on, for example, the Orion region and see the hot stars next to hotter pieces of dust. Oh, I should play the video. It's really hard to see, but the little bright blue pixels, I don't know if you guys can see it, but there's bright blue pixels, and those are just these stars, really, really hot stars. So why is this important? So first of all, it helps us better understand things like interstellar radiation fields and how they work. This will then lead us to better understand the interstellar medium's magnetic fields, which is something that's been long misunderstood, and we still don't know what's going on there. And this will lead to things like polarization models and how the ISM, I don't know, changes the angles of stuff. I know someone else is working on it, so it's great. And my favorite, star formation. We all want to know how a star works, right? Something that's really cool, and I hope we can find out soon in the future. So in conclusion, there is a really good correlation between stellar radiation fields and the 3D dust temperature map. Basically, what we're doing is calculating the stellar radiation fields for each of the reddening distance bins and summing them over one temperature distance bin to get the equivalent amount of information. The next steps for this project is an error analysis, because you can never escape uncertainties. Radiators transfer on the dust, which basically means if you have a star here, a piece of dust here, and a piece of dust behind that, the piece of dust further away will feel slightly less radiation from the star because of the dust in front. It'll absorb some of it and re-emit it. Additionally, we're trying to look for other data sets with hot stars. So while Gaia is really, really good, it doesn't capture all of the hot stars in the galaxy, and we're hoping to use other catalogs and take their data as well. Additionally, we're also trying to test how far we can take this analysis. Like I mentioned before, the further away we go, the more information is captured inside of each of these distance bins. So we're trying to see the further and further out we go if this correlation still holds. And additionally, future projects that I hope can stem from research like this is, first of all, a simulation of the re-emission caused by the stellar radiation, which you can use to recreate the dust temperature map at higher and higher resolutions. And additionally, we can search for undiscovered star formation regions by looking for different correlations between the stellar radiation and the reddening that is present. And thank you very much. Any questions? Yes.
So in your graph for the second method.
Yes. Sorry. Which one? Orion A, B? This one. Okay.
The good one. Yes.
This one. This is Perseus. The Perseus star formation.
Could you
Okay.
explain the anomaly at the bottom of that? Or the back end of that?
You mean the single point in the bottom left? That's probably just from an area with really, really low reddening. That is, Python counts is still not 0. Or it's just a really, really cold area of the dust. I should mention this plot is plotting the stellar radiation value times the reddening over the dust temperature times the reddening. So it's basically a really cold piece of dust is also receiving less stellar radiation. We could, but obviously we don't want to tamper with the data too much as well. So this is exactly what we get based on the density of the reddening and the density of dust that is there and the dust temperature map that we're getting. Any other questions? Yes. So the reddening is basically just how much dust is there. So if I were to just compare the stellar radiation plots with the dust temperature map, you can already see it's you wouldn't get that much of a good correlation. And additionally, we don't really care if there's no dust in that region, right? Because we're trying to compare the dust temperatures that you would obtain from stellar radiation versus the dust temperatures that my supervisor calculated from Planck emission data. Similar concept. So basically, if we were to project these stellar radiation values onto the dust, the reddening gives us like the density of the dust. So basically, how much of the temperatures is captured by it. We did also try to manually just select areas where there is dust by just saying look for values where there is reddening where it's not 0, and take the values from the stellar radiation and the dust temperature before. Not that great results. And we realized that multiplying it by the reddening and basically just getting the data that's already given to us from the reddening gives us the best results, which is really, really good. It shows that there is physics there, and it's really, really cool. Yes.
So your hope for this approach is to be able to predict. It should be relatively clear what's happening in terms of dust or energy. What is the predictive power of the model?
Predictive power of the model.
Okay, so you're finding a correlation.
Yes.
Very good correlation.
Yes.
That means that the model is close to
Yeah, yeah.
And what can that tell us?
So my method is basically confirming that the dust temperature map works, right? It is using Planck emission data that's kind of old. We're hoping for new missions in the future. One thing that we've been exploring specifically with this is searching for undiscovered star formation regions. So if we look at a high piece of dust, calculate the stellar radiation field, we know its dust temperature map, calculate the correlation coefficient. If there is a trend between star formation regions versus areas where there's just random dust, we could possibly say that this might become a star formation region in the future. Yes,
What was the dumbest question you get to see?
no such thing as dumb.
When they look at Sidney,
Mhm.
look at the hydrogen emission. And people report a temperature to that sometimes, and they often talk about these temperatures are really sound very hot. Like 10,000 degrees, I guess, required to get the hydrogen to
You-
release that.
Yes, yes,
You're recording temperatures that are 30 Kelvin.
yes, yes.
Those are
At the high end.
How do you have emissions that are at such astronomically high temperatures seemingly intermixed with dust temperatures that seem,
Yeah.
very above average too?
This is something that I've also questioned at the very start of my research, so don't worry. Like, I was just as confused as you, don't worry, like, this is totally normal. Basically, the dust temperatures that were calculated is from the dust itself. You get the hydrogen fusion when the dust collapses and forms stars. So eventually in that process, the star will collapse, the dust will collapse, heat up from all of the magnetic fields that are present, the gravity and the density of the dust, all of the gravity collapsing together and making it really, really hot. But if it's just stagnant gas, just kind of floating around, it is relatively cold. And you do need cold dust to form stars because if it's too hot, there's just too much energy and it doesn't have time to collide into each other and fuse into new stars. Yes? Which one? This one? Yeah. I don't really understand too much, but we know that it should work. Take my word for it. The problem is Gaia gives us galactic latitude and longitude data. So while we would have to access a different kind of database to get all of that. We could, but uncertainties. I don't want to calculate all that. Nope. Exactly. I'm hoping the computer will do it all for me. All right. No further questions? Thank you very much.
Well, I'd like to thank you very much to all three of you. That was really enlightening. That was slightly above my head, but I got bit. No. I like it when it's slightly above. Bill Gates has a new podcast called Unconfusing. I think it's called Unconfusing, something like that. And the idea being you have to be confused to seek out the answers and then become unconfused, which is anyway. Well, I wanted to first off thank everyone thank our UTM students for presenting. That was excellent, and I hope that just the beginning. Tell your friends what good time, and we got samosas and donuts. Come on. I just want to run through a few of our upcoming meetings. Our next speaker night is September. I should be able to bring this up, but for the life of me, I can't figure out how. So I've got it on my phone. It just, I hate people that read from their phones while they're, but anyway. Our next speaker night is the 22nd of September. Yeah, I'm getting confirmation that I'm correct. And it's Alfred Ng, Understanding Lunar Gateway Orbit. So as you know, Canada is involved with NASA and ESA, I think, in terms of sending missions to the events, speaker night. Speaker night. There we go. There we go. Yeah. No, that's okay. I won't go through it because you can read that just as well as I can. Our next potpourri will hopefully be in this room because this room worked for me. Equally, our old room down the hall is supposedly available according to maintenance. Who knew? It's empty tonight, so we could have been there. But hey, this is I don't know about these chairs, but other than that, the AV worked, which is all I'm really concerned with. We certainly have a public star party at Riverwood on the 26th. So if you do have telescopes and you would like to come out with your telescopes, I bring out our EV scope. It would be neat to have them set up side by side to see, let's integrate on the same target. Well, you claim yours is better. I claim mine's better. Because I'm going to walk in front of yours, jog on. What's the longest integration you've done with it? Because you figure you don't have much time with this, probably. You're going to end up having half an hour. And did you actually extract individual frames from it? Okay. Yeah, I saw the satellite one. I thought, well, obviously you're pulling them off. Okay. But so did you integrate and then just go into the scope and pull off the images? I heard they were gonna, okay, yeah, that's one, because there are a whole bunch of competitive scopes coming out that do have that ability already. So I'm sure they'll be anxious to help you out there. So again, September 26th for Riverwood. And we have, sorry.
Since if you go to the Riverwood site, it says that they're fully booked.
Right, so if you're fully booked at Riverwood, I will not say this on an open mic, but if you got there early and hung around, they won't kick you out. No, if you do bring a telescope, they do let you pass the gates. And if you are a member and you request, we do have the ability to get some, as long as it's not 200, some members in. The reason is they've established strict limits to the reservation process because during the 2017 eclipse, people went to Riverwood to view it, and they had 3,000 people show up, and it stopped traffic on Burnham Thorpe, and the city got involved, and there were drones, and it was a mess. So they've really tightened it out, and they control it very well. So you do have to register, but it does mean because it's very popular, it fills up very quickly. So I would suggest that you do one of two things: either get a telescope or borrow one from the center and then bring it back, or borrow one from your, yes. Or show up early, or just send an email to John and John will get you in. I'm joking. Send an email to John and he will find people, because you can email me, but you don't know my email and I'm not going to tell you. Okay, so with that, are there any questions, or are we going to wrap up early and eat samosas? Oh, we do have the raffle. We didn't even stop. I'm very sorry. Oh my Lord. Okay. Well, you can see that this was thrown together in a hurry. Yes. We do have a raffle for this book by Chris Hatfield. It is a murder mystery. It's set in the time of a fictional Apollo 18 mission. I happen to know because I'm in the middle of reading it. So if anyone's read it, don't tell me how it ends or who killed whom. So it's fictional mission, the Russians are involved, or Soviets at the time are involved, and they seem to be the bad guys, but I'm not sure yet. I'm just starting, so I'm not really giving much away. And if I read the jacket, it probably would tell me that much. So we have a raffle for it. It is, so if you want to stick around just for a couple more minutes, we'll do whatever. Yep. I'm sorry, say again. Oh, yes, certainly. Well, why don't you come down if you want to buy raffle tickets? They are 1 for $2 or 3 for $5. And maybe no one else will buy, so you can buy a book real cheap. Thanks. And Leo. Oh, now you want to talk.
Yeah, I want to talk. So if anyone's here to pick up their certificate, Shaquille perhaps, it's, and you too, it's they're right there. So come on down.
Okay, and I also wanted to quickly mention, I have a couple of friends who are project scientists with Unistellar, which is the company that produces the EV scopes. They're doing a live stream tonight from the Lick Observatory. They're doing a night of observing. If you're interested in tuning in, it's on the SETI Institute YouTube channel. If that might be of interest to anybody. They're gonna go all night tonight, so.
Okay. Yeah, so you're. Thank you very much. No, yeah, I have no one myself. Be more impressed if it was me, but I can't take credit. Can't take credit. Okay, well, especially with spiritual geometry, it's crazy. I remember learning. Yeah, the old trial. I remember learning like so I was like, I still don't understand that. Yeah. You went like 5 minutes to go up and line the bullets back. So you didn't have to like, I never did all. Yeah, you're in the car. No. I've been using it like every time I get a doesn't go up with it. Yeah, it's pretty well done.
No, when you're doing. Really quick, once you get it, so good. And not only that, so you do need to know about those. Yeah. I don't know. So, perfect. It'd be great. Saves you hours. Yeah. If you're like, oh, yeah. Like, that's write me a Cooper. It is. Wow. I'll be just confirming your statement. Yes. Around and if I window, are you going to? I owe you $5. So you can hear it on there. They have the same number. I owe you.